Hello, so in this video we will talk about, we'll further our discussion about phrase structure grammars, and specifically we will talk about derivation trees, and we will talk about the Backus-Naur form, and we'll talk about also the extended version of the Backus-Naur form. Okay, so in summary, what a Backus-Naur form is, it actually compacts our representation of a type 2 grammar. Okay, so what are the rules which govern the Backus-Naur form? So let's see. So first of all, it is used to specify type 2 or context grammars are specified by the fact that we can only have a single symbol on the left hand side of each production. Okay, and then what we do is we combine all productions with a common left hand symbol into one statement. Okay, and then this arrow symbol is replaced by this double colon followed by an equal sign. So double colon and equal sign. And non-terminal symbols are enclosed by this. Okay. And all right hand sides are in the same statement separated by a bar. Okay, so all right hand side means all right hand side with same left hand side. Okay. Okay, now before we move to extended Backus-Naur form and derivation trees, let's see how can we write our example which we did earlier for phrase structure grammars of signed decimal numbers. How can we write that production in Backus-Naur form? Okay, so now we have this set of productions. So this is, I just copied it from our previous work on how we generated this. Okay, so now we see that we have sign on the left hand side here and sign on the left hand side here. So all we can do is, and sign is what? Sign is terminal or non-terminal. So sign is actually non-terminal. So first of all we want to say Backus-Naur form. Okay, so we'll say sign, this is non-terminal, and then we will say this symbol, and then we will say plus and minus. Okay, so plus and minus. So then this means that this and this are taken care of by this. Okay, then we have non-zero digits. Okay, so non-zero digits again are non-terminal, represent a non-terminal element. So then we have non-terminal, this is 1 2 3 up to, okay, so I'll just say 1 bar, 2 bar, 3 bar, 4 bar, 5 bar, 6 bar, 7 bar, 8 bar, and 9. Okay, okay, then what? Then we have integer. Okay, then we have integer, and then for this integer I can say what? I can say non-zero digit, because of what? Because of this guy. Then I can say integer and non-zero digit. So integer and non-zero digit, and this is a bar here, so I can continue here. So then this guy, the next one is integer and 0, and 0 was what? 0 was a terminal element, so I will not enclose it in this sign. Okay, and then we have integer, a integer. Okay, so integer is non-terminal, a is non-terminal, and integer is non-terminal. Okay, so now this integer is now taken care of. So let's go now with decimal fraction. So decimal fraction was again non-terminal, so I can say decimal point, a, and integer. So decimal point was terminal, a is non-terminal, and integer is non-terminal. Then again bar, and the next guy is decimal point and int. Okay, so decimal point and int. Okay, then what? Then we have a. Okay, so a is again non-terminal, so a I can say 0, because 0 is terminal, and I can just say 0. Okay, and then we have signed decimal numbers. Signed decimal numbers, so this is actually my starting symbol, right? Okay, so signed decimal numbers, this is sign int decimal fractions. So sign int and decimal fraction, and then I can say sign and int. Okay, so sign and int. Okay, so this is what, this is my Backus-Naur form for this set of productions here. Okay, now let's see what is our extended Backus-Naur form set. So this extended version, this is not the only version which is available. So if you read some text, you will find some other rules. Okay, but we'll talk about only this one here, and you will see the spirit of it. And once we know the set of rules, then we can do any kind of we can modify our extension to any kind of rules. Okay, so now for extended Backus-Naur form, we have inclusion of meta characters, and meta characters are star, question mark, and plus. A group of symbols followed by a star implies that the group can occur 0 or more times. So straightforward here. A group of symbols followed by a question mark implies that the group can occur 0 or 1 time. And a group of symbols followed by a plus implies that the group can occur 1 or more times. Okay. Okay. Now let's focus our attention to the extended Backus-Naur form for this. For my sign, and then for usually, one thing I missed here, that this is skipped. Okay. Okay. So then for sign, I will just say the same thing, plus and minus. Okay. Then for non-zero digit, I just have to say again 1, 2, 3, 4, 5, 6, 7, 8, and 9. And for integer, I can say, so integer, question mark, non-zero digit. Now this guy takes care of non-zero digit and integer non-zero digit, because integer can be there or cannot be there. So question mark means that this can be there for 1 time, or this can be there 0 times. So these first two are taken care of here. Okay, and the next two we just say integer 0, and we say integer a integer. Okay, and then we have the decimal fraction. Okay, so decimal fraction, again we can say what? We can say point, and see a is there and a is not there. So we can say a question mark, and then we can say int. Okay, so it can be point a int, or it can be point int. Okay, and then we have a, and a we can have two ways. So we can either say 0a question mark, which means that it can be just 0, or it can be 0a, or we can say a, we can say 0 star, so which means 0 can be there 1 or more times, right? Okay, so this is also fine. So we can have this, or we can say this. And then we have, obviously we will have the signed decimal numbers. So we'll say signed decimal numbers, or SDN, which we called it. So see, decimal fraction is there once and not there once. Okay, so I can just say sign int decimal fraction question. Okay, so this is the extended Backus-Naur form for the same problem. So this is the extended Backus-Naur form. Okay. Okay. So now derivation tree. So derivation tree is what? A derivation tree is a representation of a derivation in a language by an ordered rooted tree. Okay, so what was a derivation? A derivation is actually a series of steps in which we can, using which we can go from one part of the set of symbols to another part of set of symbols. Okay, and starting symbol is represented by a root, and non-terminal symbols represented by internal vertices. Remember, what are internal vertices? Internal vertices are those vertices which have children. Okay, and terminal symbols represented by leaves. Leaves are those vertices which do not have children. And if we have a production A to W in a derivation, then all symbols in W are children of A from left to right. Okay, So now let's see how does this story come into play when we do our example. Remember, this is the example which we did to check whether our set of productions are right or not. Okay, so we start with our uh, starting symbol, which is sine decimal numbers. Okay, so then for this guy we have to say sine, then we have to say int, and then we have to say decimal fraction. So then sine is just negative, so this is a leaf. Then we have a 7 here. Okay, and then this guy is point here, and then we have a here, and then we have a int here. So point a int. Which one have I used? I have used point a int, this guy here. Okay, now this int point a int, this a goes to 0 here. Okay, and this int is our int a int. Okay, and then this int is our non-zero digit, and this is my 5. This a is my 0 and a, and this a is my 0, and this a is my non-zero digit, and this non-zero digit is my 5. When I say is my 5, it means it's a parent of 5. This is a parent of 0, this NZD and non-zero digit is a parent of 5. So just to be precise in the language. So now what are my leaves from left to right? Minus 7.05005, which is what I want, right? So this is the way we can find a representation of a derivation using the derivation tree. So this, as a recap, what we did was we checked the Backus-Naur form, which is another representation, a compact representation of a production and of a type 2 grammar actually. And we also talked about an extended version of the Backus-Naur form, and in the end we checked a representation of a derivation in a language through a derivation tree. So hope it was easy to understand, and thanks for watching. Hope you liked the video.